Water source heat pumps come in various sizes. You've got upflow, downflow, you've got side discharge, you've got different sizes. You see there's a console unit there in the back. A lot of schools use consoles, a lot of other buildings like that, but there are a range of capacity. I think these start all the way from a half a ton heat pump like that low-cost house has in Arkansas, and they go right on up. I don't know what the largest size of heat pump is out there, but generally what happens as the tonnage goes up in the larger ones, you start getting multiple compressors in the same cabinet. But generally you're going to find a lot of small heat pumps handling of various zones. There's a lot of different kinds of buildings and different loads that have been done. This is a retirement center. Describe this as a distributed closed loop. This is in Pennsylvania. The company was HETAC that did this originally. You can see there's a lot of land area around here. You know, a hot water, cold water distribution system would be quite expensive running that around. The nice thing about a geothermal heat pump is that you can put a heat pump system in the smallest structure with its own ground heat exchanger and own circulator with about the same price, and probably lower price system than if you had one great big central system. So you'll want to survey and look at the literature and watch the rest of these training materials to find out just what all has been done. Also been installed in greenhouses. This was, I believe, one was in either Canada or Indiana. I'm not quite sure, but they're both relatively cold climates. Energy prices would then dictate whether this technology would be appropriate. If you go to the International Energy Agency, there have been crop drying technologies developed in China. The range of applications is throughout the world, and so if you say, well, I'm in the northern climate and this won't work, well, that's wrong. If you say I'm in the southern climate and it gets too hot, then that's wrong, because it all goes back to economics and comfort. Don't feel like you're too far north or you're too far south, and whether this will be appropriate or not. One of the real advantages of this technology are the ability to integrate loads. For instance, if you have a car wash and an ice maker, and this is a service station here, the ice maker will reject a lot of heat, and that heat can be used in a car wash. If you want to control the temperature of the water in the car wash, what you can do is you can put a heat pump on there and you can raise it to the water temperature that you want or that's desired. The same ground heat exchanger then could supply the space heating and cooling system. The display cases which cool beverages and sandwiches and other things that need to be to reduce temperature, that also rejects heat. And so you can combine all these loads. So in the design process, what we're going to be looking for is jobs like this one right here. Now this one you can tell has been in quite a while, because the price of gasoline unleaded regular at that time was 92.9 cents. I think it's probably double that right now. So you can see the energy costs are going up, and this system here is probably already paid for itself and is now returning to the owner a little bit more money. In this particular case, the driveway areas are heated to keep the ice off of them. The water for the car wash there in the back there beside the flag, that water's been heated by rejected heat from the ice maker and display cases. And so that's the real one great big advantage, is that we're moving heat around, and sometimes we put it underground for short periods of time, sometimes we look at longer term periods. Now in the design, what we want to do is to be able to say, if we've got more heat than what we need, we're going to have to make sure that the piping lengths, separation distance are appropriate, so that we don't have a long-term temperature buildup, which a lot of people run around and they heard that happen 30 years ago or last year or whatever. And if that does happen, that was just a bad case of design. From that building, we're looking for a monthly load that's going to go to the ground heat exchanger. Now, that says GLIPRO up there, GLHEPRO. That is just one of about 4 or 5 different good commercial design programs. This particular program wants to know what the thermal loads are by month. Other programs want to know the heat pump run hours for a particular zone on a yearly basis. If if you're in a commercial business and you're not looking at determining that kind of information, well, your design is not complete. You need to know those because you need to be able to control that. Open systems are another class of system which has had a long history. I think in the southern climates, people like Florida Heat Pump probably moved down there because they had a lot of buildings and a lot of groundwater on the coastal areas, and they were pumping water through the system and then discharging it out. The open system means that someplace in that circuit, the water supply in return is going to be exposed to the atmosphere or to the ground, or it could be in a pond, could be in a vertical borehole. Very, very common. There's some very, very large systems which are open systems, and if you've got a good supply of water, it's non-corrosive, and you can discharge it. The big three, I call them. A lot of water, non-corrosive, you can get rid of it. You really ought to look at that as your first option. Now, there may be all sorts of reasons you can't do that. Some of them may be codes and standards and things like that, but that is a very viable option. So the open system will have a water supply and water discharge. Ponds are good. The heat exchanger in this pond can be a closed loop. It could be an open loop where you're pumping water through a plate frame heat exchanger inside the building and then extracting the heat from that pond water which is being circulated through that plate frame heat exchanger. Or the pond could have a series of coils in the pond, and there have been some very large systems both ways. There's one up in Iowa. It's about 1,000 or so tons, a big system, and it uses coils of pipe in the pond for the heat exchanger. And Water Furnace Building up in Fort Wayne, Indiana has the same thing on its building. They have a pond out there and coils of plastic pipe in that pond. So it's a very common and a very good heat exchanger system. Now, on the open system, we also have another one that we describe as a standing column well. It would be unfair not to mention Carl Orio, a member of our association and a long-time proponent of water source heat pumps, in which a hole is drilled down through the overburden, which is cased off, and then when you drill into rock, it's uncased, and you drive a steel casing into that rock which is exposed to the water which is being circulated. So now you have a circulating pump which is up at the top of the drawing. That pump then circulates water to the heat pumps, and then from the heat pumps back into the ground. The advantage that this system has here is that the water is exposed to the ground without a heat exchanger in there. And you can also increase the performance by adding a bleed to the system, which means that the water coming out of the underground formation and then comes in and is replacing some of the water in there, and that bleed system, so to speak, then adds additional capacity to the system. You need to have a little bit of experience in an area before you do this, and of course if you're the first one out there, then you need to make sure that there is some groundwater there before you drill too many boreholes. The next slide is an example of a standing column well system up in the New England area that Carl Orio was involved with. It's 225 tons. It operates very, very well. It has a main hotel and then some cottages and things like that. It's 210 tons with 5 standing column wells. Each standing column well is 1,500 feet deep, so it's a little bit deeper than boreholes that we drill in my part of the country, where we're usually drilling in clay and interspersed rock layers. Main hotel has 185 consoles, so you can see multiple heat pumps serving various loads, as well as the cottages here. So if you have a real interest in that, get a hold of Carl Orio, O-R-I-O. Not like the cookies, but pretty close.